Okay, welcome back everyone. Let's pick up exactly where we left off. Here, we're still in Module 1, working on our big picture overview of data analytics as a whole and how it interacts with styles of management and business decision making. So, here I have for you a paradigm which is kind of famous. This is one of the things that you might learn in a theory of management styles sort of environment. In some of your other MBA classes, you might see stuff like this. Cooper-Ryder and Srivastava's 1987 appreciative inquiry paradigm. Now, the stuff on the right, I understand that the picture of me is covering up some of it, but bear with me for a moment. The stuff on the right was new at the time, and they contrasted two different styles of thinking about your business or your firm and its concerns in terms of how you make business decisions. So on the left was the old school problem solving, and this is how they characterize it. I'm going to contrast these two, and then I'm going to contrast both of them with data analytics, which, lo and behold, is us in this class right now. So on the left, old school problem solving would start with something like a felt need where a problem might happen first, and then you would take that problem and say, I see that there is a need for change. Okay, you would analyze the causes of the problems, you would do some analysis and come up with possible solutions for the problem that you think you're experiencing, and then you would plan actions that you are going to take, which you could call treatment, right? Some intervention, some change in policy in order to alleviate the problem that you're experiencing in your firm. And the assumption is that your organization is a puzzle or a problem. I don't want to think of the organization as a problem, but this is copied from the famous paper, right? The organization is a puzzle that you need to solve. Well, contrast that, come up with this other idea they call appreciative inquiry. And believe it or not, I have technology. I can move myself over here. All right, so appreciative inquiry, appreciate and value the best of what you already have um, in your organization, and then envision what might be different about your organization. So the appreciating what is good about your organization obviously is not focusing on problems that already exist. It's focusing on what works, taking stock of that, and then imagining what would add to that. There are many reasons why you might want to look at things differently in a management setting. Look at what is working well and consider how you might add new things to what is working well if your philosophy is that this new stuff is going to complement what is already working well and the high quality of the working well team is going to flow over into the new team. Okay, well, let's hope that you don't take what's already working very well and add something to it that gums up the works and causes it to no longer work well. That would be bad. But appreciate and value the best of what you currently have working at your firm. Envision what you might have at your firm. Dialogue. Talk about what you perhaps should have. Notice the difference between what you might have and what you should have. Very important when we start talking about data analytics and the difference between positive and normative questions. There is going to be a big difference between what is in the data and what you should do with what is in the data. That important difference is some manner of preferences that you as a business leader have to impose on the data, on the facts, as it were, and say, this is the state of the universe. I'm in charge. I think this would be a better state if we could move in that direction. It's going to be subjective, folks, so you're going to have to come up with your own preferences and make some amount of subjective decision making at some point, but that's inescapable. So there's a might and there's a should, and then there's a what will be. This is the taking action step, right? The basic assumption here is in Cooper-Ryder's famous paper, right? A mystery to be embraced in some cosmic sense. It sounds magical. It's a mystery. Well, okay, there is something mysterious about every organization. Every organization is a little bit different from every other organization. In the Anna Karenina sense, happy families are all alike. Unhappy families, each unhappy family is unhappy in its own way. Well, organizations are also very, very different. And the styles of leadership and the things that you do in your role at an organization should be different depending on what organization you're in, but they will also be different across time depending on the state of that organization. Easy example, suppose you're on a big team and everything is going fantastically well because you've got one person on that team who happens to be an absolute powerhouse, and she does everything by herself. Well, right now, the role that you play or the role that management could play on that team is going to be very, very different from the role that they would play in the future when that individual who is doing everything eventually slows down, or suppose they retire and they take all of the knowledge and the human capital with them into retirement. Then what does your firm do? Maybe it collapses. Hopefully not. Anyway, this is a cute paradigm. Throw this paradigm out and add a third column, and let's talk about data analytics. So in data analytics, you're not so much thinking about the problems that you see on a day-to-day basis at the firm, you're measuring them. You need to summarize and visualize data that is already measurable. So you need numeric outcomes. You're going to identify variation in that data, those numeric outcomes. You can model, this is the analytics class, right? You can model the attributes of preferred outcomes and say, you know, here's what things look like on the days where our assembly line produces very, very few defective parts. That would be good. If you can identify what goes into the process that leads to good outcomes, then you can try to have more of those good inputs to get the good outcomes. Okay, model those attributes of preferred outcomes. Consider changing known inputs. Just an idea. If you know what the inputs are and you know what how those inputs correlate to outputs, notice that there's a specter here when we talk about the actions you take in the firm and the results that the firm then obtains. There's a specter of a causal relationship between those actions and the outcome, the inputs and the outputs. There's always going to be a causal link there, but it might be somewhat tenuous, or it might be something that's difficult to perceive. When you're on the ground making decisions, interacting with other people, it's usually easier to tell what is happening than when you see numeric data after the fact, right? So correlation in data does not imply causal relationships between those data, and we have many powerful counterexamples. So that's going to be a perennial topic for a class like this. The basic assumption that we have penciled in here alongside the other two paradigms is an organization has measurable inputs and outputs. I can't analyze the data in order to help me make business decisions without data. So if you're running a cash register and you're using a machine that doesn't track these exchanges and doesn't print receipts and doesn't store those data in some sort of local storage, or even on the cloud, that's data that you're throwing away. All right, and in the modern era, basically nobody runs an old school cash register that doesn't print receipts and store everything digitally, but you can imagine such a scenario, right? And that's retail. In other forms of industry, there are plenty of things that are not machine readable or measured or recorded. Now, what kind of questions can you ask the data once you have data in hand? There's a big split, which I just alluded to, between the positive questions and the normative questions. Positive questions and positive statements describe the state of the world without value judgments. That's the disconnect. In order to make certain statements or certain decisions, you will have to impose some manner of preferences, which will turn these into normative statements or normative questions. Example, raising the minimum wage leads to higher unemployment rates among young workers. Is that true? I don't know if it's true or not. It might be true. But this is a claim. You'll notice that it doesn't say we should raise the minimum wage. It doesn't say we should not raise the minimum wage. It certainly doesn't say we should lower the minimum wage. But what does it say? Raising the minimum wage leads to higher unemployment rates among young workers. And you can look at that and say, there's no subjective value judgment. There's no reflection of a person's preferences for higher or lower minimum wages in that statement. It's a purely positive statement. It's a statement of fact, which could be true or could be false, but imposes no value judgments. It's a positive statement. Example 2, an increase in government spending tends to stimulate economic growth. Okay, well, we're doing things with language here, so like leads to higher unemployment rates, tends to stimulate economic growth. You see that whoever made this statement says tends, so they're leaving an out in there as if they're hedging their bets They're not quite as certain, but this is a big topic in macroeconomics, right? Government spending as for fiscal stimulus in order to drive economic growth, specifically in order to counteract recessions. Got a couple of papers on that. It's a dubious topic again. But is there any value judgment baked into this statement? An increase in government spending tends to stimulate economic growth. It doesn't advocate one action or another. It doesn't look like it has a value judgment baked into it. It's a statement of fact, which may or may not be true. Monetary policy has limited impact on inflation. Okay, so tends in the previous example seemed to allow the possibility that it happens sometimes and not other times. Monetary policy has a limited impact on inflation. This is a statement that the impact is small in some sense. Okay, well, perhaps we need additional context, but I don't see a value judgment baked into there. There's no real dead giveaway word like should. Should implies that I have a preference. I don't see anything like that here. And the fourth one, the store sells 12,456. Hey, nice job. I would like to have $12,456 worth of merchandise on an average day. Again, a plain factual statement, which may or may not be true, but no value judgments are baked into it. Switch that. Give me some normative statements. Normative statements describe the state of the world with value judgments baked into them. So they're describing the state of the world as being something that it should be or as being something that it should not be. That's the value judgment. The minimum wage should be raised to $11.50. Notice I'm describing the state of what could be, what would be better than we currently have. All right, yeah, that's normative. And the word should is a dead giveaway. I'm not saying what the minimum wage is. I'm not saying the relationship between the minimum wage and other variables. I'm just saying it should be raised to $11.50. Normative. Government spending should be increased to stimulate the economy. Again, the word should is a dead giveaway. The central bank's interest rates are too high. Well, what is too high? That sounds subjective. Maybe I think they're too low because I'm a different person with different preferences. I don't think they're too low, by the way. The store, well, not at the time of recording. Your mileage may vary if you're watching this in the future. The store should sell at least $12,456 worth of merchandise every day. Well, certainly selling more merchandise is probably better for the store's bottom line, but the word should is a dead giveaway that we are imposing some sort of value judgments here. We're saying that it should sell more stuff. Now, when we talk about the business making more money or the business staying in business by remaining solvent, most people are going to agree with that. This is a value judgment that may not be that, it's still subjective, but it may be nearly universal in terms of everyone agreeing to it. Fair enough. Data analytics are agnostic towards the user's values or preferences. We generally look at the data. The data don't have preferences. The data do not care. The data are just a list of numbers. So we look at the data and we can make positive statements about what the average is, whether a variable is correlated with another variable, and so on and so forth. It goes to the user. It goes to you to make your own subjective value judgments about relationships that we perceive in the data if you choose to do so, or if you're in a position where it has to be done. All right. So there are many different simple things that we could talk about when we get into actual statistics. Don't get scared. Okay, mean, median, mode, weighted averages, and geometric, which is kind of an interesting one. Percentiles, quartiles, quantiles, and whatever else. We can talk about just a couple of these simple things in our warm-up, the background, basic statistics, before we get into correlation and regression analysis. So let's start with the mean. Everybody knows this thing, right? Regular old sample average. It's a pretty good stand-in for the population average if your sample was drawn randomly from a population. So is it the most important measure of location? Is that a value judgment? Is that a positive or not, normative statement? Most important? Might be normative, right? Okay, so regular mean. It's a measure of the center of a distribution. It's a measure of central tendency, as we said in the previous video. The central location of a distribution. It's the average of all the data values. Okay, well, there are many different types of averages, but the simple one that we all know and love is exactly this formula right here. So just take all of the data, xi, add them up, and divide by how many there were. If you're not familiar with this notation, the great big sigma, capital sigma, which is a Greek S, even though people say it looks like an E. Yeah, I know, but it's a Greek S. S is short for sum, as in adding. You just take all of the observations, the I subscript is for each individual observation, and you add them up, and then you divide by how many there were. In a simple example, like what we had over here, homework 1 score distribution that we saw the other day, this is easy enough to do. This is x1, this is x2, this is x3, this is x4. Add them up, divide by 105, which is how many there were, and we're off to the races. Okay, here's an example. I've got a bunch of apartments, 70 efficiency apartments, randomly sampled in a college town. So those of you in the Alabama area, make your own guesses as to whether you think that these rents are too high or too low for a town like Florence. Monthly rents for each apartment, 545, 715, 530, 690, 535, 700. Let's get the average. Let's add them all up. We could throw them into Excel and have Excel do it. We will get 41,356 for the total. There were 70 of these numbers, so divide by 70 and we will arrive at the sample average $590.80 for these apartments. Okay. Sounds affordable, actually. But these are old numbers, so fair enough. The median is also an interesting example. Moving on from the regular average, the median, if I were to order everything from smallest to largest, is the one that's right in the middle. So the median, half of the data are going to be smaller than that, half of the data are going to be larger than that. And some of you are saying, but wait, what if there's an even number of observations? Okay. Well then, there will be some number of observations on the left, some number of observations on the right, two right smack in the middle, and I'll split the difference between those, add them together, and divide by half. Divide by 2, which is cutting it in half. So the median of a data set is the value in the middle when the data items are arranged in ascending order. By the way, the thing about if you have an even number of observations and you split the difference between the two in the center is just a convention. Everybody seems to do it, but there are, in fact, competing conventions for that. So there are other rules of thumb that would say take the lesser of the two, and that one generalizes a little bit more nicely when you try to turn the median into quantiles or other things. Pros and cons. The mean and the median and the mode, which is coming up, are measures of central tendency. They're measures of the middle of a distribution. So why would you choose one over the other? Well, as this bullet says, when a data set has extreme values, the median may be the preferred measure of central location. What are the preferences that would make this normative statement something that we would go for? Well, extreme values are going to affect the average, the regular average, because it takes all of the data, adds them up, and divides by how many observations there were. But the median only cares about that observation or two observations right smack in the middle. So if I take the largest observation and make it larger, the median doesn't change. But the regular average, arithmetic mean, does change. Fair enough. So if you would like this measure of central tendency to ignore the extreme values, perhaps the median is a flavor that you should be interested in. Most often reported for annual income and property value data. That's true. That's true. So annual income is an extremely skew distribution. There are a lot of people who make really high numbers. And if we plot that data, the tail on the right just keeps going on. You have 100,000, 400,000, $1 million, $5 million. There are people way out there. Do I care so much about the distribution of the people that are way out there? I don't know. I might care about the average person. Well, who's the average person? Perhaps I care about the income that the middle person is earning. That's a pretty good way to look at the economy and say, half of people are making more than this, half of people are making less than this. That's an interesting number. And so median income is a number that is reported in almost every country. A few extremely large incomes or property values can inflate the mean. but not the median. Okay, fair enough. So try a couple of these. These are easy, right? This should be review for most people in a class like this. 7 observations, 26, 18, 27, 12, 14, 27, 19. First thing I have to do is order them, put them in order, ascending order 12, 14, 18, 19, 26, 27, and 27 again. Okay, yep, I can confirm that these are smallest to largest, ergo the one in the middle will be that one right there. The median is the middle value, 19. You can do it. I am pretty sure I can do it. So I go back to homework 1 scores. You'll notice that I've already sorted them. All right, so I did the thing. I could go to data, sort, and say sort by student number, cell values, smallest to largest. And this is the original form that this data took when I extracted it from Canvas, looking at these homework assignments, which were done in Canvas. So in order to get the median of this data, which is now oh so disastrous, how am I going to sort them smallest to largest? I just undo what I did. Right, so Excel, go back to sort. Sort by student number, no, by score. Smallest to largest, there you go. So the zeros are on top, followed by 4s, 5s, 6s, and 7s, and there's nothing else in this data. How many were there? You may have just noticed there were 105. I scroll all the way down and say, yeah, in fact, it goes down to row 106. The first row was labels. There are 105 of them. So how would I find the one in the middle? The one in the middle would have as many on the left as it has on the right. So if there are 52 observations on the left, one in the middle, and 52 observations on the right, that would add up to 52, 53, 105. All right, so let me scroll up and find the 53rd observation, and that will be my median. And sure enough, row 2 is the first, so I'm going all the way down to row 54. The median person got 7 out of 7 on this homework, which is a perfect score, and I am very happy. So that is excellent news. We already saw from data analytics, which I clicked and then there was a slight delay before it popped up. We already saw that I was able to do things like, where did it go? Descriptive statistics, and have the mean, the median, and perhaps something like a mode spit out automatically from here. So that's easy, right? Okay. In that magical case where you've got an even number of observations, the traditional rule of thumb is to put them in order, find the 2 in the middle, and then split the difference between those. So here we add one more number to the list. 19, 26 are now in the middle. All right, split the difference between 19 and 26. 19 plus 26 divided by 2, 22 and a half is going to be halfway in between those two numbers. Fine, that'll work. How about another one? 70 apartment rents. Okay, you go through. They're in order now, smallest to largest. I go and I stare and I say, okay, well, fortunately, they've been represented here in not just a list, but sort of a grid, 2 by 2 array, a matrix, if you will, of these values. And I can tell that, yeah, smallest to largest, the ones in the middle are going to be right here, 575. There are still 2 of them in the middle because it's an even number of observations. But it happens that they're both 575, so 575 plus 575 divided by 2 is equal to 575. I think I could do that math in my head. Great. Next, our third measure of central tendency in the classical paradigm is the mode. Paradigm? No, pantheon. The classical pantheon. How about that? The mode of a data set is the value that occurs with greatest frequency. It's the individual number that you see most often. It comes with a bit of a headache. So depending on the structure of the data, if you have a discrete distribution where observations can occur more than once, the mode is very easy. You just find the observation that occurs the most. If you have a continuous distribution where everything has a very fine level of precision in how it's measured, and you have a lot of decimal places behind that, you may not be so lucky as to have observations occur more than once, in which case the mode is vacuously either every observation because they all occur once, and that's crazy, or none of them are the mode, which is also not helpful, or you need to get creative in how you're going to go about estimating the mode, which is actually it's challenging, statistical problem, but it's sort of an interesting one. Okay, so the greatest frequency can occur at 2 or more different values, in which case you would have more than one mode. If the data have exactly 2 modes, the data are bimodal. If the data have more than 2 modes, the data are multimodal. Easy example, back to the apartment rents. So you go through the list of the apartment rents and you say 525, 530, 530. Oh, there were 2 of 530. So 530 is already more frequently occurring than 525. 535, 535, 535. Ooh, there are 5 of 535. So that is my new candidate for the mode. And I keep going through until I notice that 550 occurs 7 times. And in fact, 550 is going to be the mode here. So that's easy. When we get into 2 variables and we start looking at the relationship between them, before we get into scatter plots and regression analysis like we just briefly previewed in the other video, we might want to think about something like cross-tabulation. Again, very easy. So graphical representation, come up with a table. We had the tabular summary that we looked at earlier for prices of tune-ups broken up into blocks of 10 numbers. So that was pretty nice, and then we turned that into a histogram. Well, we could do the same thing in a 2x2 grid with the relationship between this variable and that variable. A method for summarizing the data for 2 variables, cross-tabulation, can be used when one variable is categorical and the other is quantitative, or when both variables are categorical, which is easier, or when both variables are quantitative, like we did with the tabular summary earlier, where we slice it up into baskets or bins. Here's an example. I've sliced everything into 2 bins, prices less than 250,000 and prices more than 250,000 for houses in the Finger Lakes area. Really, really. Again, these numbers are probably low enough that they're old, and it's New York, so I don't know that much about the property values in New York, but let's see. Home style, colonial homes, under 250,000. Because I sliced it up into a bin, as with the tabular summary we saw earlier, that's de facto a category, right? So everything that is under 250,000 and happens to be colonial style is going to be represented here. And the frequency of that occurrence, the number of them that fall into that category, is 18. Exactly 18 of the houses in this sample. Well, how many houses were there in this sample? Oh, look at that. Oh, they add up to 100. How convenient. So if this was exactly 100 houses, I've got nice whole numbers. And if I turn this into percent, which you'll notice there are no percentage symbols floating around anywhere, but I could have made the exact same table, throw some percentage logos on there, and it would be the same number. It's 18 out of a total of 100 houses represented here in that box. So another convenient example. What else? Log-style homes under 250,000, only 6, but log-style homes over 250,000, greater than or equal to 14. The greatest number of homes in the sample are split-level style priced less than 250,000. It checks out, yeah. Split-level under 250,000 is basically the mode of this array. Colonial under 250,000 is going to be the runner-up for that, and then split-level under over 250,000, 16 of those would be 3rd place. Now, you can do it in either dimension. So if I ask, which is more common, homes under 250,000 or homes over 250,000? You look and you say, well, here in the margin, when I talk about the marginal frequency and the marginal distribution, is the same idea, right? Marginal frequency, marginal percentage, marginal distribution. So when I talk about the marginal frequency, I see that 55 out of 100 are under 250,000 and 45 out of 100 are over 250,000. So most homes are under 250,000. Look at the other margin and it'll tell me something about the breakdown by home style. Okay, there you go. Colonial homes, 30 out of 100 are over here. 35 out of 100 are split level. Interesting. So actually the most common house style in this sample was split level homes. Split level and colonial style together account for the majority of homes. And then log and A-frame homes are just the remaining 35% when I combine 20% of them being log, and 15% of them being A-frame. Only 3 homes in the sample are in A-frame style, priced over $250,000. So is that some sort of a snide comment about the prices of A-frame houses in the Finger Lakes? Like nobody wants A-frames? I don't know, but perhaps that is the case. All right, so if you want to turn these into percentages, let's see, which one do we have here? By row or by column, it can be done. So if I want to say that colonial homes, all right, in the under $250,000 range are 32%. Be careful. This one will throw you off. This is colonial and over $250,000 or under $250,000 in that case right there. I need to know how many were over here in the margin and divide by that. So I've turned this into the proportion of each row that falls into each category. So for homes under 250,000, colonial and split frame are still the winners. Split frame, split level, you knew what I meant. But I see colonial homes under 250,000 are 32.7%. Okay, and split levels are 34.55%. Notice how many were in this category? 55 and 45 over 250,000. All right, so I divide the entire row by that number to turn them into row-wise percentages. I could have done it by column too, right? So when we get into 2 variables, converting these things and talking about conditional distribution and say, well, just look at the homes under 250 or just look at the homes over 250 and summarize those for me. It becomes a different beast. I'm saying if I know the house is over 250, then do you expect it to be colonial or split level or log or A-frame? One of the things that you'll notice is the houses over 250 are in fact less frequently colonial style. Under 250, 32.7% are colonial style. Over 250, 26 and 2/3% are over colonial style. Interesting. Are colonial style. All right, interesting. Split level doesn't change much. Log changes a lot, and A-frame also changes a lot. So remember, we're going to need some measure of confidence or precision to go along with a small sample like this when we try to make big statements about whether this sample represents the population. So we haven't gotten to hypothesis testing yet, but I see a difference in these numbers and I start to ask questions about whether the homes over 250 are in fact different styles than the homes under 250, which is a reasonable thing to think that that could be the case. All right, another one of these column percentages. Good. Summarizing data for 2 variables using graphical displays. So when we have one variable, we can make histograms, we can think about dot plots and a number of tabular summaries, frequency tables, many different ways of representing the one variable. When we put that variable together with another variable and start thinking about the relationship between them, maybe a crosstab like this is a clever way of going about things. Maybe you want something a little bit more complicated like a scatter plot. All right, so a scatter plot or a scatter diagram is the go-to when you've got 2 variables. It can be generalized to 3 variables and turn into a 3-dimensional plot that you could rotate and look at. It's difficult to represent graphically any more than 3 variables. So probably we won't be doing that in this class, but a scatter plot or a scatter diagram, as it is labeled on this slide, is a graphical representation of the relationship between 2 quantitative variables. So I drew a silly little scatter plot in the previous video, and you'll see it's here, it still lives here. I drew the scatter plot, I threw some stuff up on there, and I drew a regression line, a line of best fit on the scatter plot in my story about the relationship between income and education. So that's very cute. But, okay, fair enough. One variable is shown on the horizontal axis, the other variable is shown on the vertical axis. Each point in the scatter plot represents one combination of numbers, and the pattern of those plotted points suggests the overall relationship between those variables. Different things could happen. The one I drew in the previous video had a strong positive relationship, suggesting that people with more years of education have higher earnings on average. Good. That makes me happy. It could have gone the other way and we'd have a negative relationship like this here, where people with more years of education have lower earnings on average. That's rough. That would be a disaster for me. Or it could be that there's no apparent relationship between two variables and it doesn't look like they move up together or move down together. And I'll show you an example of exactly what that looks like. Homework 1, score distribution. Okay, so what would I do with this thing? How peculiar is it to think about a scatter plot of this? It's just a list of one variable. Well, it is just the list of one variable for now, but one meaningful variable. What's the homework 1 score? Okay, that's meaningful. Student number is basically arbitrary. Now, it turns out that the student number for multiple classes within each class was alphabetical order. So there is a relationship between these student numbers and the homework score. They're not totally random. But I don't believe that people who have names starting with the letter A are going to do better on the homework than people who have names starting with the letter Z. So what do? I go and I plot these together, and it's easy enough. So here we go. Student number, homework 1 score, control down, select the whole block, go up here to insert, and look at my tools up here. I've got charts, I've got line plots, there's the histogram. Beautiful, beautiful. And one of these recommended things is the good old scatter plot. This is a cool one, a bit of a fun example, because you can see some things up here on the scatter plot. And once again, I'm going to move myself. I'll put me over here in the corner on the right. So here in the scatter plot, I see, what do you see? Very few people got zeros. That makes me happy. The vertical axis represents the score. I see a whole bunch of 7s all the way across. Excellent. Very excellent. I see a bunch of 6s. I see that one lonely person who got 6.5 because they said something that I couldn't decide whether I'd give them points or not, so I had to split the difference. And then I see some 5s and some 4s, and yeah. Does it look like there's a general upward trend or downward trend in this graph? No, no, not really. And there shouldn't be, because these student numbers shouldn't be correlated with the performance of the students. That would be strange if people with names that start with A do better or worse than people with names that start with letters later in the alphabet. And so I see basically the same pattern over here on the left side of the screen as I see over here on the right side of the screen. Classic null result, no correlation here. You can do things like right-click and say add a trend line, and there it is. There's the line of best fit, which we can come back to and talk a bit more about that trend line. Ooh, set intercept. Display equation on chart. Oh, wow. We can come back and talk a little bit more about that trend line once we've introduced ordinary least squares more formally. But there it is. Okay. Very interesting. Now, I don't want to scare anyone, but I've got quite a lot of other data here. And what I have open in this Excel spreadsheet is something called, well, it's a snapshot of data from something called the National Longitudinal Survey of Youth. It started back in the 1970s. They got a bunch of teenagers and they started surveying those teenagers. So first they did a cross section. They said, okay, you're all teenagers. It's the 1970s. Answer all of these questions. Boom, cross section. I've got an observation for every person in the sample. But what happens if you do it again 5 years later? Well, now it's panel data. Maybe the first time you just call it repeated cross-section, but it is a longitudinal study. So we have many observations of these people following them through later life, starting in the 1970s, and this slice is, well, actually, I believe starting around 1980, 79 or 80. This slice is from the year 2000. And you'll see that those people who were teenagers are now age 39, 40, 43, 40, 38, 37, 41, 37. Interesting. They've got a bunch of ages. So I'm going to pop up here to the top bar. I'm going to say data, nope, sorry, insert. Maybe I want to do something clever, like a column or bar chart. Yeah, that seems like a good idea. A histogram would seem like a good idea. Combinations, okay, very interesting. Well, yeah, let's do one. Let's do a clustered column, more column charts. Where's my regular old histogram? Ooh, scatter plot, not probably appropriate here. Not what I'm looking for. Do I have some data other than, yeah. Insert, recommended, chart, no. Did a quick cut because I realized I had this thing open in compatibility mode, which doesn't work. So let me try that again. I'm trying to make a histogram of the ages of the people in the sample. So I go over here to age, which I hope you can see, and select all of those, go up to insert histogram. There it is, right here. So regular old histogram. This one is not particularly attractive because, of course, Microsoft will do its automatic thing as far as choosing the bins. Now, a note on the itty bitty tiny labels down here, if you can read them. It says square bracket 35 comma 36 square bracket. The square brackets mean that that number is included. The open brackets mean that that number is not included. Now, the ages in this data are real numbers, but we tend to measure our age as just integer age. You say, well, I turned, in this case, somebody turned 35 or 36. They're just going to say that they're 36. As a result, these bins, if you want them to stop at 35 or 36, well, there are going to be a bunch of people on that line, and we do have to specify whether that is an open or closed interval on the right or left side. Anyway, these gaps in here are quite unattractive, so I'm going to go down to the bottom. Let me zoom it just a bit more. I'm going to go down to the bottom, this 36, right-click, Format Axis, and we can do some other things, like I could specify that the bin width I would like to be exactly 1. Seems like a good number when your age is only going to vary by 1. You see here that 35 and 36 are still in the same bin, but then I've got 36 to 37. This is people who are 37, 38, 39, 40, 41, 42, and 43, and so on. And there are other things you can do to move around the histogram to improve how it looks, and, for instance, to make 35 and 36 not represent in the same bin. But I was just looking for some sort of an indication of what their ages are like now that we are effectively 20 years into the survey. Some of them are already in their 40s. So they started the survey perhaps in, say, 76, and were teenagers at the time. Hence, National Longitudinal Survey of Youth. Their age at this time in the year 2000, which is the 20th year in the original longitudinal data, hence time period being 20 here, and I've got individual unique identifiers for everyone, variables like gender. Their age is not that interesting. The one I'd like to see, because I have it and it's fascinating, is if there's a relationship between their years of education and their earnings now that these teenagers from the 1970s are in their late 30s and early 40s. Let's find out. So here's S, years of school, 12 for high school, 16 for college, and 20 for a PhD, 18 for a master's degree. Here's earnings, which is in thousands of dollars, old numbers, right, from the year 2000. I just want to see if there's a shape to this. So I'll highlight both columns. And to be fair, I really should zoom in a bit more, right? I'll highlight both of these columns, go up to Insert, and grab a traditional scatter plot. So this is it. It's a bit different from what I drew on the whiteboard in the other video, but as you see, there is an upward slope. We can fit a line to this and say perhaps whether there is positive correlation. In fact, you know what? I can't resist. So I go in, add trend line, there it is. And I can do one more thing, set intercept display equation on chart, very impossible to read. that equation there. Bring that over here for me, Microsoft. Thank you. Thank you, Microsoft. Interesting. So this line has a slope of 1.87. You'll see it's written in slope-intercept form. Y is equal to mx plus b. Easy peasy. The slope of 1.87 means on average the earnings are 1.87. It's really 1.88 if we round, higher for each additional year of education. That doesn't mean that a year of education causes their earnings to go up. It may be that the high performers, the people who are going to get high earnings, are also choosing to get higher education. But the link is there. And of course, you can see interesting things about the shape. You might consider pausing the video and just staring at this for a moment. There are interesting things about the shape where I see all of these people who have 12 years of education, and look, some of them are actually very high earners. Look at these people over here with 16 years of education, regular college degree. Again, some of them are high earners, but there are a lot of people in each of those buckets, high school and college degrees. There are not that many people with, say, 13 years of education. That's a bit unusual. Perhaps I would like an explanation for why it's 13 or 15. 16, 17, 18 master's degrees are doing well, and sadly, the PhDs are not doing visibly better than the master's degrees by very much, and there's much less variation in these numbers as well. So there's plenty to say about whether the top of the distribution is really moving linearly in the same way that the bottom of the distribution is doing. We can also ask whether this line of best fit is fitting, for instance, people with very low levels of education. They're almost all earning more than the line says that they would. And again, over here on the right, I notice that the people at the bottom of the distribution are earning about the same regardless of income, which is very interesting as well. Are earning about the same regardless of income. Are earning about the same regardless of their years of education. The bottom of the distribution seems to be kind of flat. Of course, I don't expect anyone to have negative income. That would be really, really bad. So it's natural that there's a lower bound here. And I do see, here's your bachelor's degree. I do see this upward swerve at the end of the data, right? Bachelor's degree, master's, and PhD. There are no PhDs making, say, less than $10 an hour. That's good news for me. All right, so interesting enough. Notice also that the shape of this data is not that nice tubular shape like I drew on the whiteboard or like we had illustrated here in the slides. Reality is usually much more complicated than what we see here. So, okay. Scatter diagram and the line of best fit. Please do not, the one thing that I would impress upon you the most is do not confuse correlation with a causal relationship. And in economics, we make a big fuss about all of that. But it's just universally true that the correlation we see in the data doesn't tell me whether Y caused X or whether X caused Y. I notice, for instance, on days that it rains, which it does sometimes here in Florence, Alabama, I notice on days that it rains, many people, including my colleagues and other students, are carrying umbrellas. And I start to wonder if people carrying umbrellas somehow manifest the rain into the atmosphere and cause it to rain. So if I don't want it to rain, I think we should ban umbrellas. And if I want it to rain more, so suppose we're in a drought, just mandate that everybody carries an umbrella. Well, that's not going to work. The rain and the umbrellas are correlated, but clearly it's the rain causing people to carry umbrellas and not umbrellas causing it to rain. So you can't play that game and try to stretch correlation into a causal relationship. The causal relationship needs to be something that's justified outside of what we observe in a spreadsheet full of data. Statistical independence is much stronger than the usual notion of two variables being not correlated. Statistical independence occurs when two variables truly have no relationship. So the umbrellas and the rain are related. They are not independent. They are what we would call dependent. But independent variables like the student number in the other data set and their homework 1 score, do you think there's any relationship between the homework 1 score and somebody's name, where it arrives in the alphabet? I know that there is a causal relationship between their name and their student number. I don't necessarily think that that student number and the name have any relationship with their homework 1 scores. Perhaps they do, but it's a pretty good candidate for two variables that, even though they occur for the same people simultaneously and there's a structure there, I don't think there's any correlation. I don't think there's any relationship really between your student number and how you perform on that homework. Statistical correlation, correlation, two variables are related with each other, hence correlation. Captures a limited amount of information about dependence. It actually just captures this linear dependence. The line of best fit that I put on a scatter plot is exactly what correlation is going to capture. And so on the other slide where we said most important tools, and we said something about OLS and correlation. Let me tab back to here. If this line of best fit is perfectly flat, slope of 0, then there's no correlation. And if it's anything else, then there's non-zero correlation. And that's without making a hypothesis test about it, but this line and its slope are just correlation with the units put back on. Correlation is always between 0 and 1, or negative correlation can be as low as -1, which tells you something about the strength of the dependence between two variables. A correlation like 1 is really strong dependence, linear dependence, and a correlation of 0 is no dependence. I just kind of used the wrong word. It's no linear dependence. That's weaker than true independence where there's no relationship at all, because I can come up with nasty examples. I'll do one. Nasty example. Okay, so draw some new axes, and I'll give you a scatter plot. Okay, in this case, you see that there is a relationship. It's an inverse U shape. But because I've drawn it this way and I imagine it doesn't just go up and it doesn't just go down, it goes up and then it goes down. If I try to fit a line being very different from a curve, if I try to fit a line to this data, perhaps the line of best fit is still something like that and it's perfectly flat and it tells me that there's no relationship between these variables. Correlation only captures a linear subset of dependence. So imagine that we take the true information in the data and we boil it down to just a first order concept, whether it's sloping up or whether it's sloping down, the simplest possible way to look at the relationship. That's correlation, and the line of best fit is exactly the same type of information. It doesn't tell us anything more or anything less than correlation. It just has units put back on it. And in this case, the line of best fit for these earnings as a function of years of education had a slope of 1.88, we'll call it, saying that each additional year of education corresponds to, on average, 1.88 higher earnings. And I think I said that these were, thousands of dollars across the year. I realize now that this earnings variable, I believe, is dollars an hour. So there's a wage variable and there's which is earnings, and there's an income variable in here, and I've forgotten which is which because it's not that interesting, right? So anyway, 187 more if it's dollars an hour for each year of education. Of course, knowing the units in a business decision-making environment is going to be very important. And if they're off by a factor of 1,000 because you've forgotten whether it's annual income or whether it's earnings per hour, then you probably need to go and check that. Today, here, not a big deal. All right. Statistical correlation captures a limited amount of information about dependence. Can you reiterate what I just said that it captures? It captures only a linear dependence, only something boiled down to essentially the slope of that line. Do the data slope up together or do they slope down together? If there's curvature, that's lost. If there's anything like this fan shape, you'll notice how things on the left are all closer together and things on the right are further apart. That is also lost by correlation. Much of the relationship here is lost. So, pros and cons of presenting something like a scatter plot. Scatter plots will tell you everything about the relationship between these two variables because I can see all of the data. I might have to learn how to read what a scatter plot is telling me, but it's quite simple and it loses nothing. It replicates the full information of the sample. Turning that into just correlation is a convenient way to boil things down as long as we don't make mistakes in interpretation. Good. All right, here's a simple example. It's kind of fun. Panthers football team. Which Panthers? Don't know. It's a textbook example. The Panthers football team is interested in investigating the relationship, if any, between interceptions made and points scored. Well, this is fun, right? So I suppose if you know anything about football, then I don't have to tell you that an interception is a really good thing when you get the ball from the other team. And an interception is a really bad thing when you give the ball to the other team. So in this case, I see that the number of interceptions, 1, 3, 2, 1, 3, and the number of points scored in that game, you would think if you're getting the ball from the other team, you should score more points. If I take this data and I look at the slope of the line and I find that the line is flat, meaning we're getting the ball from the other team, but we're not making any more points, I, as a coach, which I would never be, by the way, but if I was a football coach and I saw that, I would be perturbed. I would be disturbed. I would say, how is it possible that we're getting the ball and we're not scoring any more points? Somebody is doing a bad job. You might say that they're dropping the ball, but that would be a terrible pun. So I look at the data and I plot it. I throw up a scatter plot and I put a line of best fit on it, and I see that in fact, yes, those games where we made the interceptions, we got the ball from the other team, we scored more points, and I am happy. All right, so the slope of that line is kind of for each additional interception, you earn this many more points on average. That's also an incredibly useful number because that tells me with each additional interception, how much can I predict? What are the returns to an interception? So um, that's an interesting number in its own right. Here you see we could go from something like 16 to maybe something like 22. So on average, 6 points. 6 points for each interception. That's excellent. Okay, so every time you get the possession, you can turn that into points. You're doing well. Scatter diagram indicates a positive relationship between the number of interceptions and the number of points scored. Higher points scored are associated with a higher number of interceptions. The relationship is not perfect. Yeah, that's true. All plotted points in the scatter diagram are not on the straight line. You could even stretch this one notch further and look at this game in particular. You'll notice that this game is below the line of best fit. Now, there are only 5 games. Don't read too much into it, but you can look at that and say, for the number of interceptions we had, we performed badly during that game. It's below average by our standards, right? They gave us the ball and we fumbled it. Something happened. All right, so this is great information. The steps of the scientific method are very similar to the steps that you would follow in any business decision-making context. The steps of the scientific method, which you've probably seen in a high school class or at some point along the way, can be represented a lot of different ways. So this is just one of the ways of stating those, but it always starts with something like asking a question. All right. You have to start with some idea about what is important. And in a business environment, it may be, in the modern era, it may be feasible to just try to record everything that happens and have a huge amount of data, but that may not be optimal. So you may need to make some decisions, ask some questions, meaning decide upfront what data you think is interesting and how it might be interesting. Are the people working on this assembly line related to the quality of the product that comes off the assembly line? Perhaps. Well, if so, then collect information. Start gathering data about what's happening there. You can record things. You can say how much did we produce on this day, what proportion was defective, and who was working. This is all machine readable information that can go in a spreadsheet and you can turn it into real stuff. And then formulate a hypothesis. So, simple example of hypotheses, even though we haven't started hypothesis testing, could be numerically represented in the data. My hypothesis for the football team we just looked at might be that they don't earn any more points. when they get the ball from the other team. And that's a terrible hypothesis because it sounds like the Panthers suck. But the alternative hypothesis might be that they do earn more points when they get the ball from the other team. Okay, well, then I go to the data and I throw the data into some sort of a very simple methodology like ordinary least squares. Estimate that line, look at the slope of the line, compare it to 0 in terms of statistical difference, and we'll have something like a t-statistic, which will tell us how far the slope of that line is from 0. And if it's very different from 0 and I can reject the hypothesis that they don't earn any more points, then I just learned that they're doing a good job. And if I can't reject the hypothesis that they're earning no more points, then I have concerns about how the team is performing. So formulate a hypothesis, more on that in the future as we move further along into regression. But the hypothesis will be a set of numbers or a particular number that you want to hold up to the data and say, I think it might be this. And then the data will come in above or below, and we make a comparison with some sort of statement about confidence. I think that the data are too far away from my hypothesis for the hypothesis to be reasonable. Something like that. That is the test, right? So your hypothesis gets compared to the data. You test your hypothesis. You'll notice if you reject a hypothesis, if you come away thinking, yeah, this data really does not support that prior belief that I had, or if you come away thinking that the data is perfectly consistent with that prior belief that you had, then you have a decision that has been made. The result of your test leads you to believe that you are getting more points when you make an interception, or you're not getting more points when you make an interception. That could lead you to believe that you are earning more money for every year of education, or you're not earning more money for every year of education. Spoiler alert, I'm pretty sure you're earning more money for every year of education, so that's good. The conclusions that you make from that analysis could be a little bit more than whether you reject or fail to reject a hypothesis. The conclusions are going to manifest in the context of your business, and then communicating your results with your peers, other managers, other leaders in the business world is going, possibly not with your competitors, but that is the last step in the scientific method, which sometimes for academics is, publish your results. But the point is, after you make conclusions, they need to be shared with the team that is going to be able to act on what you have learned about the environment where you're operating. So this is great. Immediately applicable to data analytics in the way that we're studying it here. Kind of nice. All right, so we're going to stop this video, again, slightly over an hour, before we get into the next example, which is drawn from Chapter 4 in Stock and Watson. Very, very famous textbook, again, and it has to do with ordinary least squares. So at the risk of getting into math, we will stop it here, and I'll see you in the next one.